So the theory that we're going to study is called VSEPR theory. Okay? So remember, electron groups are around the central atom. They're either bonds or they're lone pairs. And my molecule is going to be most stable when all of these electron groups are as far apart as possible, because they're going to repel each other. We don't want those electrons next to each other. So I want to keep them as far apart as possible. And so the theory that helps me keep that in mind is VSEPR. And VSEPR stands for valence, shell, electron, pair, repulsion, and then theory. So the valence shell, those outside those valence electrons, those pairs, because you either have a lone pair or a bonding pair, are going to repel each other. So we're taking that idea, and that's how we're going to be able to predict these geometries. Right? Since all electrons are negatively charged, they're going to be most stable when they're separated as much as possible. Because remember, a negative repels a negative. So the resulting geometric shapes, arrangements will allow us to predict our shapes and our bond angles for our molecules. All right, so here's the idea. Here's my central atom. These are the two electrons making a bond. These two are making a bond. These two are making a bond. This guy and this guy don't want to make a bond like this, where they're right next to each other. They want to be as far away as possible. So because these electrons are going to repel these electrons repel these electrons. So these are electron groups, these three bonds want to be as far away as possible. So that's why I don't see something where it's like, here's my central atom, and here's a bond here, and here's a bond here. These two guys don't want to be right next to each other. They want to be far away from each other, okay? Like this. All right, so let's talk about our electron groups a little bit more. I've used this word, but remember, an electron group is just a group of electrons, okay? So the Lewis structure predicts the arrangement. So my Lewis structure is going to predict the arrangement of those valence electrons around the central atom. So here's my Lewis structure. Here it tells me these are lone electron pairs, these are bonding pairs. So now I know where all my electrons are. That's what my Lewis picture tells me. Okay? Each lone pair of electrons constitutes one electron group. Okay? So this is one electron group, one electron group, one electron group, one electron group, one and one. So every lone pair is an electron group. Now we don't care about all of those. We only care about what's on the central atom, okay? But just know if it's two electrons and it's by itself, it's a lone pair, it's an electron group, okay? Each bond constitutes one electron group, okay? Regardless of whether it's a single, double, or triple. This is one electron group, this is one electron group. So you almost want to think of attachments. One attachment, one attachment. Doesn't matter if it's a double bond or a single bond, this isn't two electron groups. It's one electron group, because it's one bond and one bond. It just has a difference in what type of bond it is. So if we look at the nitrogen, because we always figure out our geometry based on the central atom. So it doesn't matter about these other atoms. So we look at the central atom, we say how many electron groups? He has one lone pair, one single bond, and one double bond. So he has 3 electron groups, okay? If you can count the electron groups, then you'll know if it's 3 electron groups, what is that geometry, okay? So first we're going to talk about the molecular geometries. These are my parent geometries, okay? These are kind of like my beginning geometries. There are going to be 5 basic arrangements of my electron groups around a central atom. Okay? Because I can have a maximum of 6 bonding electrons. I can only have 6 things on my central atom. Not everything can have up to 6, but 6 is my max. So remember when we were talking about expanded octets and being able to have more things on the central atom, the most it can have is 6. Okay? So if I have 6 maximum electron bonding groups, then I'm going to have 5 different basic shapes. Okay? So each of these basic arrangements results in 5 different shapes. So we're going to learn 5 different geometries. Now when we talk about these, we're going to be talking about their perfect shapes. Okay? There might be some deviations, and I'll hint at the deviations as we talk about each shape. But in order for us to talk about our 5 basic shapes, we're talking about the ideal setting. Okay? Now, for molecules that exhibit resonance, it does not matter which resonance structure you use, because they'll all end up having the same geometry. So just pick the best one. If there's 3 equivalents of the best one, then just pick one of those. But as long as you pick the best structure, doesn't matter if you pick any of the other ones that are equivalent to that best structure, just pick one and go with it, okay? So if it has resonance, don't get stuck up on that. All right, so let's start talking about our 5 molecular geometries. Now, these molecular geometries are kind of like our parent geometries. And so what that means is they don't care if this is a bond or a lone pair, they just want to know how many are total. We're going to talk about some sub-geometries that fall underneath this that differentiate if this is a lone pair or if these are bonds. So right now when we talk about these 5, these are kind of like the parent, the umbrella. So these are our big main categories, and then I'll talk about your subcategories. All right, so in the next lecture, we're going to start with our first electron geometry.